Hello everyone, we are the group made of Juan Sebastián Malagón, Juan Sebastián Neiza, and I, Jonathan Rivera. We are going to present our project Multiple Instance Learning with Quantum Kronecker Kernel. The use of machine learning has become very popular in the study of cancer for various reasons. One of the most studied areas is processing of pathological images, because these images are a vital tool in the process of diagnosis and prognosis for any type of cancer. However, using them is very complicated because they are too big to be used in a neural network, and one could try to reduce the size. This would be an error that would lead to the loss of relevant information for the analysis of oncologists. Because of that, we have different learning strategies like multiple instance learning, where the image is fragmented into patches. The patches are analyzed independently, and with the results, a conclusion is given on the whole picture. It is a strategy that has become very popular because it allows working with pathological images, but generates lots of information compared to the use of the complete image. Then, a new method of integrating the information of the patches or instances is proposed, called Quantum Kronecker Kernel. For this project, we use the pathology section of the medical nest. The set corresponds to images of colorectal cancer classified into 9 different phenotypes. The data is divided into training, validation, and testing sets of sizes 90,000, 10,000, and 7,000 respectively.
Our methodology is based in the next pipeline. The idea is to take an image, pathology image, and divide it into two patches of the same size. Now we train a pre-trained BGG to classify that patches. With the pre-trained net, we extract the embedding of the whole image and the patches. Yeah. With the representation of the whole image and the patches, we use different methods to contrast the results of our kernel method. We use the min kernel and the concatenate kernel. Also, we train using the whole representation of the whole image. And finally, the machine learning method used to implement that kernels is a supervector machine. Now, our quantum Kronecker kernel. The idea of the Kronecker kernel is that we can represent a whole image with the interactions of the features of the representation of patches of that image, or better called instance. In the graph, we can see a circuit that can be used to represent that kernel. U1 represents a unitary operator that encodes the representation of the first patch, and U2 encodes the representation of the second patch. So we know that the representation or the whole circuit, the whole operator, is the Kronecker kernel between the both operators. So we have the Kronecker kernel between both representations. That's our phi mapping function. So to get the kernel, we use our phi mapping function of one image and the inverse of the phi mapping function of a second image. And we are going to measure the state 0, 0 that encodes the value of the dot product of both representations. That method allows us to obtain the similarity with a kernel method of both different images. This method can be used to get the grand matrix, and with the grand matrix, we can train a supervector machine.
After training the neural network, we start with the hyperparameter search. We run 25 experiments with 2 repetitions of each one. The hyperparameters that we used were the L1 and L2 regularization factors, learning rate, batch size, and embedding size. Thanks to this search of hyperparameters, it was possible to obtain 83%. On the other hand, it was necessary to make a different search to minimize the size of the representation and to be able to execute it in a quantum computer. The size of this embedding was R4, and the result was 69%. Next, we implement our proposed algorithm, making use of multiple instance learning, but in a quantum kernel. The performance was lower, and it was assumed that is because the patch is very large with respect to the image. The time required for this execution is also higher than the classical methods, due to the limitation of quantum computers and their simulators. According to this, we can conclude that the quantum Kronecker kernel method does not give the best result. For that reason, we recommend to make a model using more image per image. However, the limitation of quantum computers must be taken into account. Thank you for your attention.